Hello, dear visitors of DataFest. My name is Nikolay Nikitin. I am Research Fellow of National Center for Cognitive Technologies, and today I want to discuss the applicability of evolutionary optimization for structural learning of composite models. Also, I want to present the implementation of this concept as a part of FIDOT framework. Before we will start analyze the composite model concept, let's discuss the data-driven modeling approach. In fact, the recipe for building a data-driven model is quite common. The main difference from the classical model here, of course, is the presence of data itself, by which we will identify the model. At the same time, the model itself doesn't have to be only statistical or machine learning model as it is understood in most cases. Next, we need to define a loss function that sets a scolarity metric for the model with respect to the data. Finally, choose an optimization method by which we can effectively and as quickly as possible minimize the loss function. So with these simple steps, we can achieve the high-quality solution for many complex problems. Data-driven models can be classified depending on their structure. On the one hand, there are classical models that have a rigid structure. Usually, they are expressed in the form of compact simple expressions, functions, or equations. For example, the equation for hydrodynamic model are presented at the slide. On the other hand, there are some so-called pure data-driven models that have soft structure identified by data. Such models are usually built from a large number of low-level non-specific blocks connected together and allowed to approximate the different complex functions. One example of such universal approximator is a neural network. However, there are also interesting models between them, models with so-called flexible structure. As it can be seen from the figure, is something between fully data-driven models and classical models with rigid structure, so the advantages from the both approaches can be combined. To describe the practical implementation of the data-driven models with flexible structure, we propose the concept of composite model. Composite model is a heterogeneous model that consists of several types of model. As can be seen, the composite model can consist of equation-based models, numerical models that are specific for some domain area, and some other models, for example, machine learning models, automated machine learning models, and other variants. The structure of the composite models usually can be represented as directed acyclic graph, and also some simple cases of composite model structures can represent the simple ensemble of models with single level or several levels. There are several properties of the composite model can be highlighted. First of all, the composite model have a fractality property. It means that submodels inside the model can also be a composite model in their character. For example, the presented structure of composite model consists the atomized composite model that have 4 blocks in its structure. And also, as you can see, this model contains some automated machine learning model, domain-specific model, and it moves us to the second property, the interpretability of the composite model that can be achieved by the involvement of the interpretable submodels inside the composite model. For example, the equation-based model is interpretable itself, so if we involve it into the composite model, then this component of the model can be interpreted. And if all components of the model are interpretable, we can interpret the composite model itself. And of course, we can control the degree of interpretability that should be achieved during the identification of the composite model structure. The identification of the data-driven model structure can be achieved by structural learning technique. It means that the structure of model can be composed from the low-level blocks. This concept is applicable to different types of models. For example, the neural architecture search is an example of structural learning for the neural network. It can be considered as combinatorial optimization task, but also structural learning can be applied for not network-based models, for example, for composition of algebraic functions, for partial differential equations, for the ensembles of machine learning models, or the pipelines of machine learning models. So this concept can be adopted for the different types of models, including composite one. There are a lot of state-of-the-art instruments that allow to solve structural learning problem for the machine learning pipelines. It's usually considered as AutoML problem. For example, the framework TPOT uses genetic optimization to build the optimal scikit-learn model pipelines for the specific task. There are also solutions from Google, AutoCAD, H2O, and MLBox framework. However, they are all directed to the identification of relatively simple problems and cannot be applied for the identification of the heterogeneous models. The reason why all these frameworks are preferred to work with the relatively simple models is quite obvious. It can be explained by the very high dimensionality of the composite model identification problem. Since we have a lot of subjects for method training, it's the structure of models, structure of link between them, hyperparameters of the models, the preprocessing of data, etc. It is impossible to solve the optimization problem directly. So the expert-based heuristics should be involved into the structural learning problems to achieve the better result of the model identification. In the figure, there are four approaches for the structural learning are analyzed. The simplest one is the expert-based approach, when the human solve the model identification problem. It's the common way for the development of the classical domain-specific models based on equations. The second one is a machine learning approach, when the model itself is identified automatically, but the tuning and construction of model is done by expert. And the more advanced version of this approach is the automated machine learning, when the generation of pipeline and tuning of model inside it is done by some optimization algorithm. And the final step is automated machine learning with expert knowledge involvement that allow to solve the high-dimensional structural learning problems, and potentially it allows us to achieve the better quality of the modeling results. To interpret the structural learning as optimization problem, we can use the following formulation. In this equation, M means the model that represents the nodes of the composite model. The L represents the links between these nodes, and P represents the hyperparameters of each model in each node. In the figure, you can see the structure of simple composite model that describes this formulation. Also, the other part of the optimization problem is objective function that we want to use. And as you can see, we can split the objective function into two sub-functions. It is the quality-based objective function that represents the quality of the simulation using the composite model with specific structure, and the structure complexity metric that allow to express the negative impact of the overcomplicated structure of the model. For example, we have too many nodes, too many links, and of course it can decrease the final quality of the simulation. As you can see, there is also data involved into the calculation of the objective function, and in this case we should separate our data sample into three parts: train sample, test sample, and validation sample. And the structural learning should be done using both train sample for models fitting and validation sample for the evaluation of quality metric. And of course, we should have some observations, that is ideal modeling results for our case, that allow us to calculate the described quality metric. And of course, this problem can be considered as both multi-objective case, when we want to find the compromise between quality and structural complexity. And also it can be considered as single objective optimization when we use the structural complexity as a penalty for the quality. We tried to solve this optimization problem using evolutionary methods. Evolutionary methods are based on the concepts of natural selections, and it can be adopted for the composite model structure identifications in the following way. In the evolutionary optimizations, we have the concept of chromosome, the set of genes that represents the phenotype of the individual. In our case, the chromosome represents the structure of the composite model, so it is its nodes, links between nodes, and the parameters of each node. And we used the evolutionary operators, crossover and mutation, to mix and modify the structure of each composite model that allow us to obtain the better individuals. And the phenotype is expressed by the objective functions, so quality-based objective functions and structural complexity-based objective functions. And each individual can be assessed using this matrix for phenotype. We choose the evolutionary approaches to solve this problem due to the several advantages of this technique in the comparison of other optimization methods, for example, like Bayesian optimizations or particle swarm optimization. It's the balance between the exploration of the search space and exploitation. And it's especially important for the composite model since the search space is quite large and complex. So we should both explore the new structures of the model and refine the existing structure with the high values of objective function. Also, the stochastic character of the data should be taken into account since the processes that we want to simulate can be stochastic itself, for example, some environmental process. So it should be taken into account when we develop the optimization method. Also, the discrete and continuous variables both exist in the representation of composite model structure, so our optimization method should be effective for both of types. The evolutionary approaches are well suitable for the search of Pareto optimal solution for the multi-objective case that can be obtained from the formulation with the separate quality metrics and structural complexity metrics. And also evolutionary approaches can be modified and expanded, for example, to the co-evolution concept when you have several populations that also allow to achieve better results in complex cases like composite model structure identification. If we want to adopt the evolutionary approach for the structural learning of the composite models, we should resolve several issues. The first is the generation of initial populations. It can be solved in several ways. The first is the growth of the individuals from the scratch, so it's a pure random approach. The second one is the usage of some initial assumption, some initial structure of model that can be used for each individual if initial population, or used as a basis for the stochastic modification that allow to obtain the initial population with the specific properties. Also, the specific crossover and mutation operators should be chosen or implemented to obtain the better convergence. The pseudocode of the simple evolutionary composer, so it's a program component that allows to solve the structural learning problem, is present. It consists of several steps: the initialization of the population, calculation of the metric for each individual and population, and then application of different evolutionary operators. There are several crossover operators can be applied for the directed acyclic graph of the composite model structure. The simple one is the subtree crossover that really just changes the subgraph of the first individual to the random subgraph of the second individual, and vice versa. The more advanced version of the crossover is one-point crossover. It finds the parts of the model structure graphs with the same topology and then find the common point of each graph and then change the part of graph under this point. It allows to obtain more diverse result and in the same time to preserve some structural patterns of each individual. So later the experimental studies that allow to compare the quality of result obtained with each crossover and with both crossover together will be presented. Allow us to achieve better result but also increase the search space. The third type of mutation is not devoted to increase the size of model structure, but it's devoted to reduce, since we can have overcomplicated structure of the model and the stochastic reduction of the structure can be useful. And as you can see, reduce mutation just removes the some models or subgraphs from the structure. And the other mutation that is specific for our implementation of composite model is data enrichment mutation when we add additional data sources to the secondary model in the graph. So if in common case the secondary models receives just the probabilities or values from the models of previous level, the data source allow also to involve the original data into the modeling process, and it also can increase quality, but the cost is more complex search space that can be hard to find the global optima. Despite we propose the various approaches to mutate or crossover the individuals, the overcomplicated structure of the model is still can have place after all evolutionary steps. And of course, the stochastic reduction of the and simplification of the structure is not enough, so we introduce the regularization operator that allow to simplify the structure of composite model without additional cost of the fitness function calculation, because calculation of fitness function is very computationally expensive, since we should fit each model in the graph for each new individual, since the topology of model was changed. However, even if the topology of model was changed, some parts can be used without retraining. So we can extract the subgraph from the composite model structure graph and evaluate its quality independently, like it is a separate composite model. So the regularization operator allows us to decompose the graph into the set of subtrees, evaluated, sort by the objective function, and then add the best individuals into populations and remove the overcomplicated individual if the subpart of the graph obtained from this individual is better by the objective function. Also, if we start to speak about performance, the caching technique was implemented as a part of this evolutionary approach. Since we shouldn't refit all the models inside composite model if the topology was changed, it's just a part of the model set that was affected by this topology change. So if we have shared cache for the all individuals in the all population, we have some pool that we can use to simplify the training of new composite models. And you can see some experimental results. The green line is the evaluation of models inside composite model without caching. The red line is the evaluation with the local caching, when we have separate cache for each chain but have no any multimodal cache. And the blue line is the implementation with shared cache, when the parts of model structure graphs from each individual are saved together in some global pool, and it is used when we want to evaluate the objective function for the new individual. In this slide, the result of experimental studies with different implementations of evolutionary operators are presented. As you can see, the different types of mutations was evaluated separately and together, and the most effective mutation is reduce mutation, because it allows to achieve the higher quality of the models with the less number of generations. But of course, it's just the result of very complex search space, so it's also practical to use different combinations of mutations, because when we have a lot of generations, it converges in some similar point. Also, as you can see, for the crossover, we have also similar results, but several crossover types have a bit better results when we have a lot of generations. And the implementation without crossover at all, that is popular solution, for example, for some narrow architecture search problems, is not effective for composite models, so some crossover should be used. And the effectiveness of the regularization operator is also investigated. And as you can see, the solution without regularization, that is represented in green color, is not effective, but any implementation of regularization allows to obtain better results. In the bottom part of the slide, the visualization of the evolutionary process is presented. You can see the candidates individual, the best individual after several evals, and the growth of best value of objective function found during evolution. Now let's discuss the application of the composite model for the practical purposes. The composite model itself can be applied for different problems. For example, the classification problems can be solved using composite models. The example is a credit scoring problem that really just a detection of the suspicious credit applications by the set of features obtained from the transactions or from applications. The other case is the composite model for the time series forecasting. There is an example for C-surface height is presented, and it's interesting that different scales of the process can be represented as a part of composite models. As you can see, the trend and residual of the C-surface height time series are forecasted independently. Also, the composite models can be interpreted in Bayesian sense. As you can see, the composite model that consists of several Bayesian networks can be used to solve the synthetic media data generation. But of course, we have a problem how to apply the developed evolutionary approach for different kind of models. It can be achieved by the interpretation of these various models as a nodes in the graph of composite model structure. For example, these sub-networks can be interpreted as independent models that should be connected in the appropriate order by the evolutionary techniques. The important aspect of the composite model identification is the tuning of hyperparameter of these models. There are several approaches can be used to achieve the result. The models can be tuned individually, just final model in the graph can be tuned, and all models can be tuned together. According to the experimental results, it can be concluded that independent tuning is not quite effective, since if we tune just M1 model without passing the data through the M3 model, the tuning results will be non-optimal, and the quality of the whole model will be decreased after the tuning. So there are several models should be tuned together to achieve the efficient result. Also, the different methods of tuning can be used, from the simple grid search to the advanced methods. Last, for example, faster web-to-web optimization algorithm proposed in the noted paper. But of course, the choice of the method depends from the computational complexity of the model fitting. Since if the model is very complex and have a lot of submodels and links, it will be hard to use the complex tuning technique. The performance problems is a really crucial point for the composite model analysis and identification. If we want to make these processes more predictable and interpretable, the performance model can be used to achieve the better result of optimization for the specific time constraints. As a conceptual example of the dependence of model quality from the time of optimization, the Pareto frontier optimization time model error is presented. As you can see, it's obvious result that more time we spend, the better result we can obtain, but we can obtain better result with the specific time constraint if we choose the better strategy. And the strategy can be chosen using performance model that connects the time of evolutionary algorithm evaluation with the hyperparameters of this algorithm. In practice, it's impossible to build the performance model for the evolutionary algorithm without the building of performance model for the composite model itself. And really, the performance model for the composite model can be built from several performance models for the submodels from the structure of composite one. And as you can see, the performance model can be simple and takes into account just number of the data in initial sample, but also it can take into account the number of features. So we have a two-dimensional model for the single model, for example, machine learning model like LDA and random forest, for example. And we can use the additive principle to obtain the composite performance model and just some set of performance model with the specific parameters that depends of number of inputs of each model and the size of data that we use to compose the model. And the red dots in this figure represents the empirical results, and the surface represents the model-based approximation. As you can see, it has some prediction ability and can be used to predict how much time should you spend to fit your model and how much time should you spend to achieve some result by evolutionary algorithm in the worst case, if the early convergence will not be achieved. Now let's take a look at some experimental study results that are obtained using the practical open source implementations of the proposed evolutionary approach, the FEDOT framework. The FEDOT framework can solve the problems of classification, random variable regression, time series forecasting, and other. So let's look into the examples. First of all, we run the experiments using the several synthetic data sets, and it's really interesting situation since it's necessary to have not only data, for example classification, but also it's good to have the reference chain that is global optimal for this data. So we implemented simple synthetic data generator that allows pass the data through the chain and obtain some synthetic results that can be used to check the convergence of structural learning by evolutionary algorithms to the reference tree structure. And as you can see at the right figure, the evolutionary algorithm labeled as GP, that stands for genetic programming, allow us to reduce the tree distance to the zero, since the random search is impossible to do it because the search space is too large for it. The other example is inspired by a real problem of credit scoring and can be considered as classification task. After the application of evolutionary algorithm that was described before, we obtain such composite model that consists of 5 models and 3 layers. As you can see, the comparison of metric for composite model obtained by feeder framework with other different solutions like random search, XGBoost, TPOT, HTO, and MLBox AutoML frameworks allow us to conclude that proposed evolutionary approach allows to achieve better results in the same optimization time. The other set of examples that was used to validate the implemented approach is the regression benchmarks from PMLB library. It is a well-known set for the automated machine learning techniques validation. As you can see, the FEDOT allow us to obtain the competitive results with state-of-the-art TPOT. And as you can see, the typical example of obtained model is presented below. It consists of 9 models organized in 3 levels. And this model allows to achieve quite good result too. The other interesting case that we are analyzing during the experimental studies is the oil production forecasting using the hybrid model that consists of machine learning regression models used to forecast time series based at set of lagged features, and the capacity resistance models that allow to forecast oil field productions for some oil field. In the bottom part of the screen, you can see the result of production forecasting obtained by CRMIP model. So it's balance equation based model, the ML based model, and hybrid model. And the forecast quality metrics allow us to say that an evolutionary optimized hybrid model allow us to achieve the best result. Finally, it's possible to conclude that composite models is really a useful concept for many applications, and the evolutionary optimizations is quite effective way to find the optimal structure of these models. Also, the simplification of the evolution results is really important, and it's impossible to achieve competitive results without it. Finally, it should be said that we try to implement all described methods, algorithm, and techniques as a part of open source FEDOT framework, and we will be glad if someone will contribute their own ideas into this framework. I pass the links to repository and also some additional information about our research team that are developers of this framework. So thank you for your attention. If you have any question, I'll be glad to answer it.